Today's experimental mathematics seminar speaker is the one and only Neil Sloane, who will talk on exactly in his birthday. Today, October 10th, 1939, he will speak, and as a birthday present, usually the axiom of this seminar is 48 minutes. So he was granted 7 extra minutes. And also after, people are welcome to say a few words to wish him happy birthday. Go ahead, Neil.
Thank you, Doron, and thank you for that present of those 7 minutes. That's I have to do share screen. All right, share screen.
You're already sharing, Neil. It's okay.
You can already see it, yeah.
Okay. Well, now I've really messed it up, right? If I'd... Always something goes wrong at the beginning. So what should I do? I can see... all I can see is...
Just go on and talk, yeah, so...
good. Now I can see
the
screen.
screen. We can see your screen.
Okay, good. Okay, surprise in a sequence, and I'm sharing it correctly, and it's big enough. You can see it. Okay, good.
Looks perfect.
Okay, thanks. All right. So there was some terrible news 2 weeks ago. Eric Angelini passed away at the age of 73. He was always one of the most brilliant contributors. His sequences were always clever, witty, they made you laugh. There were no others like him, and he submitted over 20 years, 1,500 sequences. A typical sequence, he would give a sentence describing the sequence itself, a self-describing sequence, and you would think that there's no way that could define a sequence. But then he would add and pick the lexicographically earliest sequence with that property. And more precisely, it's an LES sequence, and officially LES means the lexicographically earliest sequence of an infinite sequence, that's important, of distinct positive numbers. Distinct is very important, satisfying the property. So a sequence... one of his earliest sequences, the sequence has the property that it describes the positions of which terms in the sequence are primes. And so it couldn't begin with a 1, and you pick the lexicographically earliest such sequence. Now, it couldn't begin with 1, because that would say the first term was a prime, but 1 isn't a prime. So it can't begin with 1. So you try 2. Well, 2 works, it turns out, so you have to take 2. You could run into a contradiction later and you'd have to backtrack. But very often in these constructions, the greedy algorithm works. 2 is not ruled out and 2 works. And 2 tells you that the second term is a prime. All right, so the next term, it has to be distinct from 2 and it has to be a prime. So it could be 3, and in fact, it must be 3. And the 3 says the third term is a prime. So that we can't go 2, 3, 4 because 4 isn't a prime. So you go 2, 3, 5, and so on. And there's the sequence. If you look at my slides, they actually have links to the sequence, so you can find out more details about them. He contributed many classic sequences, including the famous comma sequence that I talked about in the first lecture in this seminar of the year, and other people here have worked on. And if you don't know, his son, Lorenzo Angelini, made a wonderful video, an animation of this sequence. It's on YouTube. It's well worth looking at. And then there are a number of other sequences that I've talked about in the past, and many others that I haven't talked about yet. And here's another typical example. The sequence has the property that if a digit is even, the next digit is bigger than D. And there's a graph of it. Strange looking sequence. And Eric said that when he discovered the OEIS, he thought it was the 8th wonder of the world. He liked it very much, and we will miss him. The official talk, I've got 4 sections. The first section, Doron, you may remember 10 years ago at the my 75th birthday, you had a conference at DIMAX about sequences, and many people attended.
And by the way, I offered Neil to organize another conference, but Neil refused. He just preferred to give a talk on his birthday. Thank you.
Yeah, I did refuse, but a talk is easier. So 10 years ago, I said that sooner or later we're going to need to hire a managing editor because we're getting so many submissions. There's too many for the volunteer editors to handle. And that is even more, we didn't have any money at the time, but that's even more so today. We're really swamped with submissions. We get, I guess I should emphasize this, we get about 1 million hits a day. We have a very strong group of volunteer editors, but 170 volunteer editors who are very, very conscientious and brilliant and clever and very good at understanding what the contributors are trying to get at. But they're finding it increasingly difficult to keep up with the submissions. When I looked at the submission stack this morning, it was up to 264, and so I attacked it for a while, attacking both ends of the stack. At the beginning of the stack, there are new sequences submitted by the experts, the editors-in-chief and the other people who are very familiar with the OEIS, and they're easy to approve. The far end of the stack, there are those submissions that have been sitting around for a month or more waiting to be approved. And for that, I have to make the final decision, and that's something the managing editor will have to do to decide. They're borderline sequences. It takes some judgment to decide whether they're appropriate for the OEIS or not. And, of course, the contributors tend to get rather upset if they're rejected, even though we explain to them very carefully why this is not appropriate for the sequence. So I'm hoping we'll be able to find somebody who's qualified to run the submissions process, to keep track of the submissions, what the editors are doing, to resolve questions about the difficult sequences and the qualifications. It's pretty clear what we need. Someone who's fluent in English, fluent in mathematics, and fluent in computers, and hopefully familiar with some of the languages that we use. The main languages in alphabetical order are Maple, Mathematica, Pari, and Python. And we have hundreds of thousands of computer programs. And so those are some of the qualifications. Another important qualification is that this should be a simpatico person, someone who's quick to understand what the person is getting at and is furthermore tactful and so on. And an unfortunate requirement, I mean, not unfortunate, it's just the way things are set up, it has to be a US resident, otherwise we can't pay you. And we don't yet have the description of the job on the Foundation website yet, but that should appear within the next couple of weeks. And of course, one of the responsibilities of this job is to be an interface with the community. If you were to think of the world of mathematics as a balloon and the real world as another balloon, these two balloons don't touch very often. And the OEIS is one place where they touch, where people who are not professional mathematicians or anything, but are interested in mathematics, and they have some ideas and come up with perhaps with a sequence. Through the OEIS, they get in touch with the mathematical world. And in fact, several people have told me that it was through the OEIS that they became mathematicians themselves. So there are responsibilities of this job, but there are also rewards. And one of the rewards is that you get first dibs on the new sequences as they come in. And the rest of this talk is based on 3 sequences that came in this summer. And I could easily have added 5 more. There's no end to the flow of these. So the next topic, the first mathematical topic, is covering the sequence with straight lines. Suppose you have a sequence of in the OEIS, A1, A2, A3, and so on, take a piece of graph paper and put down a dot for each term. So the first term, A1. Let me take the primes as an example, because that's really a very interesting example. Take the prime points. The prime points are the red dots on the left. So the first prime is 2, and so there's a dot whose coordinates are 1, 2. Second prime is 3, so there's a dot at 2, 3. So those are the red dots, the prime points on the plane. And the question is, if you'd like to, we'd like to draw lines through them so that there's a line that touches every prime point. How many lines do we need? What's the smallest number of lines we need to cover all these points? And here are the first few values. Suppose you want to cover the first 5 prime points. So you want a line that goes through these 5 points, 2, 3, 5, 7, and 11, the 5th prime. Well, you can cover them with 2 lines. You can there's an obvious line of slope 2 that goes through 2, 3, 5, and you can join 2 and 7 by a line. So the 5th term, the number of lines you need to cover the first 5 primes is 2. And there's the beginning of the sequence. And it's a covering problem, because you can pick any line through 2 points, and you want to pick the smallest subset of those lines that covers that. And one of the famous NP-complete problems is minimal set cover. So you can apply that here. And Max Alekseyev found a nice implementation of set cover. And he extended this sequence out to 410 terms, and it looks like this. This is the number of lines you need to cover the first n primes, where n goes up to 410. And, well, what is this curve? Dan Asimov said it reminded him of the Devil's Staircase, the Cantor function, which I've got on the right there. And you can see there's some similarity, though I don't really think I don't know. What is that curve? Of course, you can do this for other sequences. If you take the number of divisors function, d of n, which is on the average about log n, and do the same thing. Ask how many lines do you need to cover the points n, d of n. And here's a graph, and you can see that the number of lines you need is constant for quite a while. And I think that's a sign that this is a very irregular function. Number of divisors is extremely irregular, of course, even though its average is log n. And you can sort of see that this is roughly like log n. So the basic question, which I really think is worth looking into, what's the relationship between the growth of the original sequence and the number of lines you need to cover it? Here's the same thing for phi of n. And phi of n is pretty close to n. It's a much smoother function, and you can see that by this curve. And again, what is this curve? The original question that prompted this investigation was, I got an email from Dominic McCarty, who did the same thing, looking for the lines that go through the points, but his points were the number of lines to go through the points. It was a recursive definition. You start off with 0, and then A of n is the minimum number of straight lines needed to cover all the previous points. So it's recursive. Here is a picture of some of the lines. 6 lines you need for 23, 20 for the first 23 terms. And here's the graph. This should be an interesting graph. I would like to know what it is. There's a lot we don't know about this. I think interesting problems to work on. And if you're looking at going back to the prime sequence, if you want to know asymptotically what's going on, Well, one of the things you need to know is how many points can you get on a line? So this is a separate sequence, a different sequence. You can say, what's the lexicographically earliest line that contains exactly n prime points? So, for example, if you want a line with 3 points on it, as I showed you in the previous slide, 357 is a line of slope 2 with 3 primes on it, and that's the first one. How do you tell if it's the first? You look at the biggest prime, and you want to minimize that. If you want 4 primes on a line, then take the line through the points 5, 11, 17, and 23. It has slope 3, and there's no smaller line that has 4 points on it. Of course, you have to be careful with this, because some lines go on for a long time before they hit a large prime. So Max Alekseyev worked out some terms of this, and he was careful to use lower bounds on how the primes are, so he could be sure that once he'd gone out far enough, there were no more primes on the line. So this is the sequence, and it's sequence A376187. I was surprised when I worked out the first 20 or so terms, and I was surprised to find there's a line with 20 primes on it, which is quite small. It's shown in this graph. Where is it? It's a line of slope 6. 6 is obviously a good slope for primes, for catching primes, because primes tend to be 6k plus or minus 1, and slope 6 seems like a good idea. There's a line of slope 6 which has 20 primes on it, and the biggest prime is 509, and they're actually the blue dots on this picture. But there's a parallel line which also has 20 points on it, which are the red dots, and they're slightly bigger. So here are 2 parallel lines, each of slope 6 and each with 20 primes on them. And actually, you won't be surprised to learn that the blue dots are congruent to 5 mod 6, and parallel to them there's another 20 points. Not a simple translation, of course, but there they are. And the other ones are congruent to plus 1 mod 6. And you could contrast this with the famous question of how many primes are there in arithmetic progression, which is something that has been studied by a lot of famous mathematicians. And it's known that there is an arithmetic progression with 20 primes, but you have to go out quite a long way to reach it. You have to go out to that term to get a prime, to get 20 primes in an arithmetic progression. But that's not any good to us anyway, because they're not on a straight line, because the gaps are not constant between those primes. Anyway, I thought it was interesting to compare those 2 results. And the other day, Don Rebel said that he's found lines with 54 primes on them and slope 12, and another line with 79 primes on it of slope 12. Obviously, after slope 6, slope 12 is a good thing. What happened to that? Oh, I see. That's a slide that I was using to create the caption to that figure. All right. All right, the third topic, unless there are any questions on lines through points. Chernobyl didn't have any dampening, and it blew up. Well, we have, in the mathematics world, we have sequences that blow up, the most famous of which is the harmonic, what's called the harmonic series, which is a pretty obvious sequence. Take 1 plus a half plus a third plus a quarter, ... plus 1 over n. What's the value of that number as n gets big? Well, you might think that it'll converge to something because these are little tiny numbers. But in fact, if you remember that the sum of 1 over n is like the integral of 1 over n, which is log n, then you won't be surprised to learn that the sum of the first n fractions is very close to log n plus some correction term. So Remy Sigrist in Strasbourg suggested, let's dampen down this, stop it blowing up, by putting in dampening rods or dampening coefficients into the sum. So instead of 1, we'll put in we won't take the whole of that term, we'll take a fraction of it. We're always going to take an integer fraction of the term, and we're going to take a half of that term, as it turns out. And so the modified sum is going to be 1 over a1 times 1. We've put in a dampening coefficient into the 1, which will be 2. And then we'll dampen down the half, and so the new sum will be the sum of 1 over a sub n times n. And what we're going to do is keep the sums always less than 1, just less than 1, and choose the coefficients, the dampening coefficients, to be, thinking of Eric Angelini, to be the lexicographically earliest sequence of numbers.
I have a question, Neil.
Yes.
Just want to make sure. So in this example, x1 is 1, x2 is 2, and so on.
There's no x's yet. The sequence we're dampening down is 1, a half, a third.
Oh, that's a multiplication symbol. I'm so sorry.
Yeah. In this font, the Helvetica Neue font, it doesn't have a good dot in it. The dot appears in a funny, asterisk. There's no good multiplication sign, so I've used an X. I'm sorry. Yeah, that says 1 over a1 times 1, plus 1 over a2 times 2. Sorry. And then, so let me do it here. We're going to choose the lexicographically earliest dampening coefficients. So we start off. The first sum is 1. It's 1 over 1. Well, we don't want it to be bigger than 1 or more, so we'll put in a half. We'll take 1/2 of that 1. So the first sum will be, the first dampening coefficient will be 2, and so the sum will be 1 over 2. And the difference from 1, we've got to keep it under 1. So this is 1/2 away from 1. So D1 is the difference between the current sum and 1. That's where we have to fit the next term into. Then for n equals 2, we want to find a number, a2, such that when we add 1 over 2a2 to a half, we're under 1. So a2 can't be 1 because a half plus a half would be 1, but it can be 2. So we take a to be 2, and then we've got a half plus a half of a half, which is 3/4, and the distance to 1 has shrunk to, d2 has shrunk to 1. And the next one, we're going to add some fraction of a third to it. And we can't add a whole of a third because that would take us over 1. But if we take a half of that third, half of the third is a 6. The new sum is 3/4 plus a 6. It's 11 over 12. And the distance to 1 has shrunk to a 12. So we keep doing. That's the sequence. And here it is. It's the A sequence here, the dampening coefficients. They go into the denominators. And I showed you 2, 2, 2, but then it starts to grow. And in fact, it grows doubly exponentially. And the sums, well, I showed you a half, 3/4, 11 over 12. The next one is when we add 1/4 of a quarter to 11 over 12, and we get 47 over 48. And again, that has the property, the curious property, that the sum, it has the form that if the denominator is e, the numerator is e minus 1. Rather a surprise. 47 over 48. Next one is 1199 over 1200, and so on. And Remy checked that is true all the way out for the first 36 terms. And these terms actually are pretty large because they're growing. I'll show you. They grow very fast. So one question is, how fast do they grow? Another question is, what are these numbers? Is it true? Is it always true that the sums have this form of c minus 1 over c for some integer c. And surely someone has studied this question before. Since it wasn't in the OEIS, maybe not. But it would be nice to know. I hope somebody can point me to some paper by some numerical analyst who looked at this years ago. Gauss, maybe, somebody. You can get a simple recurrence just by following the definition. If you look at the requirement on the definition, the requirement of the definition is that the n minus first sum, let me just put the cursor there, s of n minus 1 plus 1 over a of n times n has to be less than 1. And if you take that and turn it around and make it upside down, you find that you get two equations relating these constants, that a of n is related to d of n minus 1 in that way, and d of n is related to d of n minus 1 in that way. That's just a restatement, really, of the definition, but it's a useful fact. Then they do grow doubly exponentially, and I'm going to skip that because roughly speaking, the denominators grow like 10 to the 2 to the n, doubly exponential. Now, Remy managed to prove his theorem, his conjecture, that indeed these sums, when you follow this process, they do have the form of an integer minus 1 over an integer. And he proved it by induction, and it's not totally straightforward to do this. The induction hypothesis has to be strengthened. It's not just enough that dn, the difference from 1, is 1 over an integer. You need a couple of other properties. It's 1 over an integer en, and the ens have to satisfy the property that en is divisible by all integers less than or equal to n and by the previous e. And if you take that as your induction hypothesis, then it's not difficult to prove his theorem. Now, you could do this for any divergent series. So I just set it up as a general problem. Suppose we have a diverging sum. Let B1, B2, ... be such that the sum of the BI's diverges, goes to infinity. And then we look for the lexicographically earliest positive integers, the dampening coefficients, that keep the running sums less than 1. And we've looked at several examples. I just showed you what happens with 1 over n, the harmonic series. You can do it with the primes. You can do it with the diverging series 1 plus 1 plus 1 plus 1, ... And there we actually find that the dampening coefficients are a known sequence. It's sequence, one of the earliest in the OEIS. It's Sylvester's sequence A58. And if you take the diverging series to be 1 plus 2 plus 3 plus 4, now we put the integers in the numerator. All right, that's obviously going to diverge. Then again, we get two known sequences as for the sequence for the a's and the denominators, and many others. Here's what happens if you take the primes. Again, I was surprised that this was not in the OEIS. You want to dampen down the sum of 1 over the primes. You know that sum of 1 over p diverges because that's really the integral of 1 over x log x, which is log x. So log x clearly blows up. So this is worth doing to the primes. And the sequence you get of the a's goes 1, 1, 2, 3, 5, and is doubly exponential. And it was not in the OEIS. A surprise. And if you look at what this means, and also it's interesting, the epsilons, the difference between the numerator and denominator of the s's is not always 1 in this case. There are 2. The fourth and the sixth epsilons are 2. And then it appears that they're 1 from 6 onwards, from 7 onwards. But that's just a conjecture. There are a lot of questions here that I think would be well worth looking into. And if you look at what this means in the end, it says that in the limit, the sum is 1, And what we've gotten is what's called an Egyptian fraction, a sum of 1 over integers. And we're using the property that the denominators must be multiples of the primes, successive primes, and so on. And again, I thought somebody might have looked at that before, but apparently, well, I expect somebody will say, yes, that's all known. I'd like to know. If the b's, the diverging sum, are integers, then you can prove that, in fact, S, the sum, does have the property of being of the form E minus 1 over E, and you can give recurrences. But in general, we just conjecture that there's a constant such that if n is large enough, they have that property. Then I'm going to put the slides on the Experimental Math Seminar website so you can look at them. I don't really have time to go through them in detail. This is, if you're taking the diverging series, 1 plus 1 plus 1 plus 1, the dampening coefficients, as I said, it's Sylvester's sequence, A58, that goes 2, 3, 7, 43, 1807, sometimes called Euclid's numbers, because each number is the product of the previous numbers plus 1, just what you do when you're proving there are infinitely many primes. So 2 times 3 plus 1 is 7, 2 times 3 plus 7 is 42, you get 43, and so on. And here it makes it clear that in this case, you're obviously getting doubly exponential numbers. If you take the b's to be powers of 2, you get numbers that have come up before in looking at generalized Fermat numbers. You get some, like the Fermat primes. Here we get the 6 of the 7 dampening coefficients are primes, nice large primes, although not as large as the ones we're going to see in a minute. We did this recursively, and then Remy Sigrist found some examples where the epsilon is not 1. If you take your sequence to be the example 4b at the bottom of the slide, if you take the sequence 7 over 6 and then 5 over 4th repeatedly, and apply this procedure, get the dampening coefficients, you find the sums are of the form En minus 5 over En. But our conjecture is that there's always a constant C, which should be 5 here, such that from a certain point on, that's what the sums look like. And so that's one way to dampen down this diverging series. Here's another way, which is not uninteresting. Bob Lyons found, or rather learned, I suppose, that it's been known for a long time that even though the sum of 1 over n diverges, if you replace n, if you read it in base 11 instead of base 10, that makes the numbers a little bit bigger. I call it U of n. U of n means take n, a decimal number, and think of it as a base 11 number, an undg number. So, for instance, if n is 25, U of n means you've got 2 11s plus 5. It's 27. It got a little bigger. And the slightly surprising fact, convenient for our purposes, is that the sum of 1 over U of n for all n, it converges, even though the sum of 1 over n diverges. And this is really follows from a classical theorem of Kempner from 1914. The sum of reciprocals of numbers that are missing a digit. And Bob Lyons said, what is this sum? And it turns out that people had worked out how to get this sum, but it's not that easy. Kempner's paper is 1914, and there's a paper of Bailey in 1979 giving an algorithm for working out these sums. If you try by brute force, you don't get very far. Brute force does not work here. And even using even using the idea of if brute force doesn't work, which is what my friend William Cheswick always says, if brute force doesn't work, use more brute force. Well, using more brute force doesn't work here either. But there is, if you use Bailey's algorithm, you can work it out. And Gareth McCachen worked out this, and we've now got as many digits as we want of this sum, the sum of 1 over u of n for all integers n. But what about the primes? This is an open question, and it's a sequence. We don't even have one term. What's the sum, the decimal value, of the sum of 1 over u of the primes? Several people have tried this and failed. Hans Hoverman sent me an email the other day. He tried hard, and then he tried really hard, and he took 1 billion terms and got the sum to be 2.89. And then he took 66 billion terms and found the sum had got up to 2.91. And he extrapolated the curve and said that, well, it looks like after 1 trillion terms, it'll be up to 2.94. And he says, well, it could go up to 3 or 20. We don't know. We don't know a single digit. All right, the last section is going to be about a nasty surprise in a sequence. But if there are any questions? So when the sequence came in, I had just been reading a very funny poem by James Fenton called God, a Poem. I'm not going to read it all because you may find it a bit offensive. It's very anti-religious. But it begins by saying, a nasty surprise in a sandwich, a drawing pin caught in your sock, the limpest of shakes from a hand which you'd thought would be firm as a rock. In short, a surprise. So here's the way it began, is that the sequence, Bill McCachen submitted what looks pretty innocent. The rule is, let me show you, here's his sequence. If you start with 1, a of 0 is 1. I think that should probably be a of 1 equals 1. There's a typo. All right. You begin with a of 1 equals 1. You're given that it's 1. The rule is, if a of n is not a prime, you double it and add 1. All right, 1 isn't a prime, so double it and add 1, you get a 3. So there's the second term, 3. Now, if it is a prime, you would say, what's the next term? If the second term is 3, what's the third term? Well, the answer is you take the third prime in the world and subtract 1. So the third prime is 5, subtract 1 and you get 4. So the sequence goes 1, 3, 4. Okay? Is 4 a prime? No. Double it and add 1 and you get 9. Double it and add 1 and you get 19. Aha, a prime. When you get a prime, you go to the next term, this will be the 6th term. You take the 6 prime and subtract 1. 6 prime is 13, so the next term is 12. And you keep going. That's the sequence. And the primes, I've put red circles around the primes. They don't appear in order. You can see 3, 19, 103, 463, and so on. So one question is, what are the primes? And when do they occur? So I asked one of our Mathematica experts and trustee, Harvey Dale, if he would kindly work out some more primes in the sequence. I just was curious to see what it was like. And he computed 289 primes, which took him out to about 100,000, 10,000 terms. But some of the primes get pretty big quickly. After 3612 steps, you get to a prime. It's the 203rd prime in the sequence, and it's 134851. So the next term, the rule says the next term is going to be the 3613rd prime minus 1. You take the prime and subtract 1, and you get 33748. Not a prime, obviously. And you double it and add 1. and you don't get a prime, and you double it and add 1, and you don't get a prime, and you keep going till you get a prime. And you get a prime after 2,225 steps, and that prime is quite large because you've been doubling it for 2,000, doubling it 2,000 times, and the prime you get is shown here. It's about 10 to the 674. And Harvey-Dale continued this, and he stopped after 10,000 terms when he got to the prime 838951. But he didn't find the next prime, and it begins 104916. And please remember that number. You're starting, that's the 10,017th prime minus 1. 104916. And now you do the same thing. You double it and add 1, and double it and add 1, and you ask, when's the prime? When's the next prime? So I cranked up one of the big commercial computer algebra systems and let it run for 24 hours. And then basically nothing happened. It just kept going. So what on earth is going on? This was kind of a surprise. It's interesting to look at a graph of this sequence. This is just a graph of 1,000 terms, and it's a log plot. And you can see they grow pretty quickly. Every so often, there's a big prime, and then it goes down. So what's going on? Well, what's going on is that we've come up against the Riesel problem, which appeared for the first time in a paper in 1956. His question is, if you start with a number and double it and add 1, how long is it before you get to a prime? In fact, do you get to a prime? Always. And he proved in this paper, which happens to be in Swedish, so it wasn't so well known, he proved that there are infinitely many numbers that don't reach a prime. And we've not reached one of them yet in this problem. When the prime, the sequence 104916, when you double it and add 1 and repeat it, you're in the sequence 1/4917 times 2 to the I minus 1 as I increases. And the people who worked on the Riesel problem knew that there were primes there. This is not an example of a sequence that might have no primes in it. There is a prime, and in fact, the people who worked on this problem had already found that there's a prime. If you go out, double and add 1, and you do that 340,000 times, you get to a prime, which is about 10 to the power 102,409. This was a surprise. But they didn't know it was the first time that it was a prime. There might have been a smaller example. So Riesel's paper in Swedish, Lars Blomberg managed to locate a copy in Sweden and translated it into English, and it's now on the internet. This paper wasn't available anywhere, but thanks to Lars, it's now attached to sequence A076337. And what he proved, Riesel, is that there are infinitely many numbers such that the sequence k times 2 to the I minus 1 contains no primes. And I was sort of curious to see how this works, and I wrote out a proof, which is in the last 2 slides of this talk that you can read at your leisure. It's not so simple. And the first example that Riesel found was the number 509203, but he didn't prove that it was the smallest example. And a lot of people have spent a lot of time, probably millions of years of CPU time, trying to prove that that there's no smaller number. And the way you do that is you pick all the possible smaller k's and you exhibit a prime. And that proves that if k is less, it would prove that if k is less than 509203, then there is a prime, and that 509203 is the smallest number such that k times 2 to the I minus 1 doesn't contain a prime. And I thought this was such an important question that it's a sequence in the OEIS. It only has one term. We're not even sure that that's right, although I think it will be proved pretty soon to be correct. They had 250,000 sequences to find primes in, and there are only 42 left at the moment. And there's a web page that reports on the progress.
These people also talk about Sierpinski, don't they?
Yes. And in fact, you can do all of what I've been talking about the Sierpinski problem. And there's an analog of McEachen's sequence that I created in the Sierpinski format. But I'm not going to have time to talk. I'm going to go back to where I was. So yes, absolutely. It's a kind of a dual situation. And there's a whole different set of people working on the Sierpinski conjecture. And there's a sequence, though, with more than one term in it, giving what are believed to be the smallest k's, such that 2 to the k plus 1 doesn't contain a prime. So there was a question. The Riesel team had proved that there was a prime in the sequence. K was 104917, remember. 104917 times 2 to the I minus 1. They proved that it does contain a prime, namely, if I is 340181. But it wasn't known that that was the smallest. And that was the difficulty in running a computer program to do that. But Lucas Brown came to the rescue. He programmed this in Python, and you can see his program in the OEIS, and he did it in Python using BPSW for the primality testing. It took 15 hours of wall clock time, and he used 24 threads running in parallel. And so that's his theorem, that indeed this particular sequence, the smallest prime is when the exponent is 340181. And so now I can draw another picture showing what we know now about the sequence. Here's 1,000 terms. If you look at, you have to go out 350,000 terms to get the next prime. So this, as a result of Lucas Brown's work, we know that there's a log plot, there's a long straight line going from 10,000 up to 350,000. And all the ups and downs of the previous slide they're nothing in comparison to this. They're just these squiggles at the beginning. We don't know what happens next. I would really like to know, is this sequence going to hit one of these Riesel numbers that doesn't contain a prime, or is it going to keep going, hitting prime after prime and getting bigger and bigger zigzags? It would be nice to know. And as I said, David, thank you. Yes, the Sierpinski analog of this, but I don't have time to. So I think my time is almost up. So I just want to say thanks to this was during the summer. A lot of people contributed to these sequences. It was something appealing about these sequences. I also want to thank all the editors and trustees who keep the OEIS running, and especially our president, Russ Cox, who's done a great deal in this year to improve the software, the lookup process, the editing mechanism, and the GUI. And he's told me he's about to make even more dramatic improvements to the appearance of the database. I could have talked about many other sequences from this summer, and here's one from Scott Shannon. Here's the graph of it. I'll stop there. Is there any questions?
Just let's unmute ourselves and give Neil applause. So So here's a chance you can take your time. Either ask questions about the talk or wish Neil happy birthday. So everybody is welcome to say something.
Yes, happy birthday, Neil.
Thank you.
Happy birthday.
Yeah, I guess this is actually the exact day, right?
Yes.
So, hi Neil, this is Don Knuth.
Hi, Don.
I recommend that you look at sequence A007731.
Okay.
But anyway, the number 85 to me is most interesting because it's a palindrome in binary.
Ah. Uh-huh.
So I don't know how easy it is for you to put that sequence on the screen.
Oh, I can probably do that if I leave the...
Okay.
But I have to share. Am I sharing everything? I think I'm not sharing. No.
Okay. So 007731.
I can see it myself.
Oh,
You're just showing the slideshow at the moment, Neil.
Yeah, I know. Ah, so if will I still be sharing if I close the keynote?
Yeah, you can stop sharing this and share the sequence.
Oh, stop sharing and reshare. Okay.
Yeah.
Okay. Stop share.
This is Hugo. I just want to wish you a very happy birthday, Neil.
Thank you, Hugo. We go back a long way, don't we?
We do indeed.
Certainly. All right. So now let me. God, how do I do share again? I'm still in Zoom. Okay. Oh yeah, and here's a green button. Okay, and I can do share, and I want to pick. But now I have to choose the right thing to share.
Yeah,
So
you have some
pick one.
sequences.
All right, share.
Yeah.
Uh-huh.
Don, is that it?
Yeah.
yeah. Okay. I just thought it was kind of interesting with respect to your age.
Yes, sir.
Yes, indeed. I see. Lots of 85s.
Yeah, the maximum is 32 85s in one sequence.
Oh, really?
Yeah, it's
Missed it.
well, I have have the right search tools. I think on
was looking
Neil's birthday sequence, we have a link to this one. Yeah.
Yes.
Okay, no, I see. I was looking for consecutive 85s. I guess you're
Yeah,
looking
yeah, they are consecutive.
32
Yeah.
consecutive?
Do you know the A number?
Oh, okay. Well,
Wait a moment.
Yes, I have it. Let's see. 98971.
Yeah.
Will you say it again?
98971.
Oh, yeah.
Oh, yes. It's quite similar to that one.
Yeah.
Yes. All right. And I see there are draft edits. So what the editor does, he clicks on that and sees it's proposed and does approve. It's a simple task if it's sent in by an expert.
Now we can all, after the talk, go approve one sequence.
Basically,
birthday
this
present.
sequence are the Jacob's tail numbers repeated 2 to the n times.
Ah. By the way, I wanted to say that even if you're not interested in applying for the job of managing editor, it's still great fun to become an editor. You really are never short of interesting problems to work on.
Yes.
so I also looked up sequence 85, which is
Oh, famous one, yes.
yes,
Yeah, of course.
It's number in involutions.
Yeah. Number of self-inverse permutations. Yes. Yeah. Yeah. Classic.
Good show.
Oh, yeah.
Jesse would be proud of you.
Huh.
And in the art of computer programming, there is a way to do asymptotics of these numbers. and John said that this will be done by a computer.
Well, asymptotics, you have to ask Andy Odlyzko for
Right.
the best algorithm. But speaking of art of computer programming, I just wanted to say that OEIS helps me about once every 2 weeks. I would never have been able to find stuff. I mean, I guess I don't have space to include all the acknowledgments I should put into it. But
I just like to say a vote of thanks to Neil for having run such a successful dating agency. One of the huge things that the OEIS has given me. I have some sequence, maybe I know what it is from my neck of mathematical physics, but if I type it down there, I found all the other contexts and the people who have been working on it, and I can go and read their papers and send them email messages. So
yes,
it's been the most wonderful contribution to my intellectual development. So thank you for your dating agency, Neil.
Thank you. That's what it's for. That's what I built it for. Yes. Yeah.
I was looking at the numbers in the talk that you gave today. So you started out with these covering problems with lines, and they were all A373, 800 something, but then all of a sudden we got to the divisor sequence, and that jumped up by 2,000, and so there must have been an afterthought to look at divisors.
Yeah. It depends a little bit on who's taking numbers off the dispenser. People tend to take a bunch at a time and then wait until they've used them up and then take another bunch. So they jump around.
Oh, I see. So you might have some recycled numbers that are very small?
No,
we don't recycle the small ones, but the ones in the current range get recycled. If a current submission is rejected, we recycle those numbers.
Right.
Well, if you claim more than one number, then you get typically you don't get recycled ones, but you get some from the end of the stack. And if you just submit a sequence without reserving a number before, then you typically get one of the last recycled.
Yes. So it's quite irregular.
Yeah, yes. And but typically there are not more than 6 or 10 in this deleted sequences list, and they are typically being reused within a few hours.
Yes. Yeah. And you can see there's a website, there's a web page on the OEIS wiki that shows all the ones that have been recycled, that have been rejected or recycled for various reasons. And it's quite a long list by October. It grows each month.
Well, we try to be consistent in our rules, what is accepted and what is recycled, and we have been a little bit more strict than in ancient times. Yeah, so
yes,
there has many sequences are in OEIS that wouldn't be accepted today. Yeah.
Yes.
But I hope that you don't kick them out.
No.
Okay.
No, we don't do that. Even if they're wrong.
Wikipedia sometimes has delete entries because it decided that the person or object is not worth it. So hopefully Once it's there, it stayed.
Well,
It stays because it's been published. If
Yeah.
a published sequence, even if it's wrong, we include it, and then if it's discovered later to be wrong, we leave it in because it's been published in the OEIS.
But if it's wrong, you put a comment, right?
Yes.
If the number is wrong. If the
the
number
most frequent reason now is that it's a duplicate of an existing sequence, or it's just a multiple of an existing sequence. And now with our tools, it is easy to determine if this is the case. And then we kindly ask the submitters to put their new material into existing sequences, because that is the big advantage of OEIS, showing connections and not piling up new sequences that differ by one number or so. It's really better to have all in one place, unless the new sequence is really something completely different. And but even then, if there is an existing one, it's better to have the material there, yes, because the wonderful thing is finding connections.
Yes. Hugo, thank you for doing all this. I know it's basically your program, right, that detects this kind of duplication.
Yeah, well, now
the
new advanced search functions introduced by Russ also finds this, but there are many submitters who are hesitant to use it because they hope they get a new own sequence. Yeah.
Yes. Yes.
Some persons do searches to find something, and others do searches a way to avoid a find. Yeah. So, but that's our daily job as editors. Yeah.
Yes.
And I'm the bad guy.
But also, as far as recycling sequences is concerned, then I think it's important that once an external source may have referenced a sequence by a particular number, that's why you don't want to be deleting it.
Absolutely.
We never delete historical material. Typically, we do not delete something that is older than half a year or so. Yeah, but everything that is in the database, we don't undo history. And the only thing that can happen is that we find later on it's a duplicate, but then it's marked as a duplicate and the reference is still there. So we are really watching not to delete any references. So this is something, if we recycle a sequence, we are constantly look, are there already links to it? So that's something we check.
Yes. Yes.
Yeah, anyway, it's an amazing community. This feeling of community, I really admire everything, combining professionals and very smart amateurs. It's really a unique community, and it's really amazing. And all these connections that you discover between disparate things. It's really, that's how mathematics progresses. That's really, so keep it up.
Mm-hmm. Yes, I'll try.
Any more wishes or questions to Neil?
Well,
okay, so thanks so much for coming, and happy birthday, Neil. And in 5 years, I hope you give another talk, in addition to the many other talks, but exactly in your birthday. And we're gonna, if it's not a Thursday, we're gonna make it a special talk exactly in your 90th birthday, whatever day it is.
Thank you, everyone.
Thank everybody for coming, and happy birthday, Neil.
Thank you. Thank you.
Happy birthday.
Good job, Neil. So,
thank you.
Thank
And
you.
the recording will be available shortly.
Bye-bye.
Bye-bye.
I think next week is the 90th birthday.
Yes, of Dominique Fart, everybody is welcome to come. And Don is going to speak for 5 minutes or more. Thanks so much for coming. Thank you. Stoyan, please close this meeting. Thank you.